Welcome back. Before I walk you through the mechanisms for E1 and E2, I'd like to take the time to briefly introduce the effect of a solvent. All organic reactions or any chemical reaction for that matter has to be carried out in a solvent medium. Okay, unless the reaction is completely gas phase, then you probably don't need a liquid solvent. But for the most cases, most chemical reactions happen in the aqueous phase. That means you do need a solvent. Okay. Now there are two primary kinds, at least for the sake of understanding E1 and E2. One of them is a polar protic solvent, and the other is a polar aprotic solvent. Okay. Protic means, it's proton rich. Okay. And aprotic is obviously the opposite, proton deficient. Okay. Now, polar aprotic solvents almost always favor your SN2. Okay. And polar protic solvents typically favor E1, SN1, and to a greater extent your E2 as well. Okay. E2 is not so much solvent dependent. It can work with a wide variety of solvents, but for practical purposes, I'm going to put these in here. Okay. So polar protic solvents typically work well in E1, SN1, and E2 mechanisms, and SN2 primarily works well with polar aprotic solvents. Okay. If you're using a polar aprotic solvent, which most likely I would try to stay within these four for the purpose of this course, because these are most likely what you would encounter in our lab. Okay. So if you're using a polar protic solvent, then this is a weak nucleophile, this is a strong nucleophile, this is a weak nucleophile, this is a strong nucleophile. Okay, this is the halogens. So among the halogens, this is a weak nucleophile. That means this is a weak base. Okay, this is a strong nucleophile, so it's a strong base. Okay. Whereas if you are using a polar aprotic solvent, then it's the other way around. Okay, this becomes the most nucleophilic. So in a polar aprotic solvent, this is a strong base, and this is a weak base. It's important you understand the difference, because write this a little better here. Okay, this is a weak base. Okay, because one of the important things that you have to learn, like if I don't specify whether a reaction is SN1, SN2, E1, or E2, when you're using the flow chart, okay, and I'm also going to give you a list of some common strong bases and weak bases, and a base is essentially a nucleophile. So if a strong base means a strong nucleophile, weak base means weak nucleophile. Okay. Well, the first thing you look at whether to go in the SN1, E1, or SN2, E2 direction is actually the nucleophile, or in other words, the base. If the base is strong, the chances are you're going to have either an SN2 or E2. If the base is weak, then you're more likely going to have an SN1 or E1. So it's the base that splits the reaction into two halves. From there, you use subtle differences in the flow chart to actually narrow it down to either an SN2, SN1, E1, or E2. Okay, so the solvent also plays an important role, as you will see when we look at the mechanisms. All right. Without further delay, let's look at an E1. Okay, now I am going to use a weak base. Okay, like maybe methanol. Okay. Okay, and heat. Okay, now heat is a very good indicator of a reaction being elimination. Okay, heat is a very good indication. It does not indicate, however, whether it's E1 or E2, but heat sure does give you a clue. And this is a weak base. Okay, now you will see that whenever you have a metal in place of the hydrogen, it becomes a strong base. When lack of a metal makes it a weak base. That's one way to remember whether a base is weak or strong. Okay, now this is a tertiary carbon substrate, right? So you got your 1 bond, 2 bond, 3 bond, and the 4th bond is your Br, right? So let me get rid of the red so that it's not in our way. So knowing that this is a weak base, okay, and we have a tertiary carbon substrate, okay, we can come to a conclusion that we are going, the fact that you have also heat, okay, there are 3 things that are in favor of an E1, okay. First thing you look at is the base, and we know it's a weak base, and this is a tertiary carbon substrate. And the third clue that you have is heat, okay. Now this is all pointing towards an E1, okay. So, but remember when I introduced the idea of E1 and E2, I said E1 shares a lot of similarities with SN1. So first thing is the Br comes off, okay. This is the mechanism, the Br comes off, which leaves you, whenever a bond is moved into another element, the carbon to which that bond was attached should get a positive charge, which is what we have here. Okay, I'm going to just circle it just to emphasize it, plus Br minus. Okay, that's one of the subproducts. Now we have 2 routes that can happen. One of them is this base is not big. Okay, we're going to look at another example where the base is really, really bulky. Now I did say that tertiary carbon substrate plus a weak bulky nucleophile is a guaranteed E1, right? But a weak base itself plus a tertiary substrate would almost guarantee you E1 as well. But so you can have 2 products, right? Remember, this is the carbon containing, it was containing the leaving group, right? So that means this is your beta hydrogen. This is also your beta hydrogen, right? Now I'm only going to show you the mechanism for one of them. Okay, now I'm going to switch the color here to maybe a blue, so it's too many reds. Okay, so what happens now here is the CH3, you know, the oxygen contains a lone pair, okay? One of them is all you really need. The lone pair comes, okay, and abstracts this hydrogen. Okay, it's important that you understand the mechanism. Okay, the lone pair comes and grabs this hydrogen, which is the beta hydrogen, and then the bond goes here. Okay, now the bond is equal to a negative charge because the hydrogen is leaving, which is what is written like this, it's leaving. This bond goes in, makes a double bond, and a bond is equal to a negative charge. This is equal to a positive charge. So the positive and the negative cancels out. So we have a double bond here. Okay. Similarly, on this side, if this hydrogen was subtracted, then this will be one of the products. Okay. If this hydrogen were to be abstracted, CH3O. Okay, if this lone pair abstracts this hydrogen, which is also beta, then this bond comes over here, neutralizes the positive charge, then you have a double bond here. Okay, so a weak base could have potentially moved it to the SN1, but it's the heat that sealed the deal. Okay, so you have a weak base, which means either E1 or SN1 could have happened, but the fact you had a heat, and heat means usually it's higher temperature. Okay, high temperatures definitely guarantees E1. So the fact that we had a heat and a weak base and a tertiary carbon substrate all favors E1 elimination. So from here, so this bond came here and this is another product. Okay, now based on the Zaitsev rule, Okay, Zayd's rule. Now we know that the more alkylated the double bond, in other words, the more centered the double bond, the more stable the product is. And in this case, this is much more inside the molecule, which leads to the fact that this is a more stable product. All right, now let's look at E2. Okay, this is also a tertiary tertiary substrate, but I am going to give you something like along the lines of this. CH3C. Now I could have done it for, okay. Now say I give you this and I don't need to even give you heat, okay. This is a strong base, but it's also a bulky base. Now what does this mean? So whenever you have a base and it contains, it looks like this, usually what this means is, from your general chemistry, I'm going to switch color again back to my red. This is the negative portion. This is the positive portion. The positive portion has no effect, whereas the negative portion is your nucleophile, okay? Now, not everything always has to be OH minus, okay? That's one of the many nucleophiles available. So this is also a nucleophile. And E2 is a single step process, right? Now, keep in mind, this side is heavily, this side is 2. So this CH3O minus, you know, this is the nucleophile, right? I'm going to switch color again just to show the mechanism in a different light here for you. So this nucleophile could grab this hydrogen, okay, and then this bond could go here and the Br could come out because E2 is a single step process. Or it could attack this beta hydrogen. Remember, this is both beta, right? And I told you the beta hydrogen is the one that gets lost in the elimination process. It could attack here, but the fact is this side is so big compared to this side. This molecule is already so big that it cannot come from this side and attack this hydrogen because of all these substituents. So this side is much more easier for it to attack. So it attacks this hydrogen, and in the process, this bond comes over here and the Br comes out, okay? Please pay attention to the mechanism. So that's why you only can have this product. You cannot have this other side product because this molecule is bulky and it's a strong base, strong bulky nucleophile. And I said a tertiary substrate with a strong bulky nucleophile only favors E2. So that means this is only possible. The same with this one. So this is, again, I could have used the same example, CH3CONA, which means the negative and the plus. The negative, okay, now in this case, you see that this is both methyl, right? So you do have a hydrogen still here, right? But this has a hydrogen, but the fact of the matter is this is too big and this molecule is already occupying space, so it's easier for it to attack this hydrogen. So it attacks this hydrogen, removes it, and in the process, well, I should have had the Br on this side, but you know what? They should come off the opposite side. So let me put the Br here, and this group should have been there. So what happens here is the Br comes out, okay? So that's why you have this. This side is also possible, but because this molecule is too big, it goes to the side which is less substituted. In other words, there's less reason for it to be stopped, whereas the other side is already big, and so for it to attack from that side. So keep that in mind, that this is a strong, bulky nucleophile, okay? A nucleophile is a base, so this can also be written as strong, bulky base, okay? So in the previous case, we looked at a weak base and a tertiary carbon substrate, so that was E1. We also had heat. Now, if it had been a weak, bulky nucleophile, you don't even need the heat. You would have already made it through E1, but because it was a small, weak nucleophile, we had to supply heat. But in this case, This is a strong, bulky nucleophile in terms of E2. And I said in my introductory thing for E1, E2 that a strong, bulky nucleophile favors E2, especially if the substrate is a tertiary carbon substrate. Okay. So that's all I had to say about E1 and E2. And in the successive videos, I'm going to actually work out a few examples and then summarize the whole concept with the help of a flow chart. And I think the flow chart should really, really help you in getting this concept right every single time, right? So stay tuned.